Good afternoon, morning, or evening. Today, we're going to talk about the evolution of CPU processing power and how it has shaped the world we live in today. The invention of the CPU, or the central processing unit, paved the way for many of the technologies we now rely on daily, from smartphones and laptops to cars, medical equipment, and even smart home devices. The CPU plays a major role in shaping modern society. It has greatly influenced our productivity, the global economy, and the way we communicate, learn, and work. One of the first CPUs ever released was the Intel 4004. Introduced in the 1971, this early processor contained only 2,300 transistors. To put that into perspective, modern CPUs today contain billions of transistors. Despite its simplicity, the Intel 4004 was capable of executing around 46,000 to 250 to 92,500 instructions per second. This may not sound slow by today's standards, but at the time, it was revolutionary. For comparison, ENIAC, which is considered to be the first general-purpose electronic computer, could only execute around 5,000 instructions per second. Not only that, ENIAC was massive. It preoccupied the entire room and consumed an enormous amount of electricity. Meanwhile, the Intel 4004 was small, efficient, and powerful for its size. This difference in performance, size, and power consumption shows how big of a technological leap the CPU presented. Interestingly, the Intel 4004 was originally designed as a custom solution for a calculator. It was not meant to be a general purpose processor. However, its creators later realized its potential and released it to the public, changing the future of computing forever. Now, let's talk about how a CPU actually works. A CPU operates by looping through three basic steps, which is fetching, decoding, and executing. This is known as the instruction cycle, and it repeats billions of times per second in modern processors. First, we have the fetch phase. This is where the CPU retrieves the instructions it needs to perform from memory. These instructions are stored in the computer's RAM, or random access memory. To explain this in real life terms, imagine a notebook. The notebook itself represents the RAM, and each page it contains instructions of instructions or data. The CPU is like a student who needs to read what's written on the pages. The bus, which connects the CPU to the memory, can be imagined as the student's hand, carrying information back and forth between the notebook and the brain. Excuse me. Next is the decoding phase. In this step, the CPU interprets what the fetched instruction actually means. It determines what kind of operation needs to be performed. Is it a mathematical calculation, a comparison, a data movement? This stage involves a key component called the ALU, or the Arithmetic Logic Unit. The ALU is responsible for performing basic arithmetic operations such as addition, subtraction, and multiplication and division, of course. It also handles logical operations like AND, OR, and NOT, which are essential for decision making and programs. For to make it short, logic gates. For example, if a program asks, is this number greater than 0, or these two values are equal? Now, the logic is processed here. Finally, we move on to the execute phase. This is where the CPU actually performs the action it decoded. If the instruction was a math problem, the ALU solves it. If it was a memory instruction, the CPU reads or writes data. If it was a jump or decision instruction, the CPU changes the flow of the program. In simple terms, Execute phase is where the CPU does the work. Together, these three steps, fetch, decode, and execute, happen continuously, extremely fast. Modern CPUs can perform these cycles billions of times per second, which explains why our devices can run complex applications, stream videos, and play games smoothly. From the Intel 4004 to today's multi-core processor, CPU evolution has been driven by the demand for speed, efficiency, and smaller size. As a as technology continues to advance, CPU will only become more powerful, enabling innovations we can barely imagine today. Now, let's talk about the rise of x68 or the x68 architecture. It came to dominate the personal computer world through the powerful combination of Intel, IBM, and Microsoft. As the 1970s progressed, the CPU designs became increasingly more advanced. Engineers were experimenting with faster clock speeds, larger memory, addressing capacities, and more sophisticated instruction sets. All of these improvements aim to make computers more flexible, powerful, and more suitable for real-world applications. One of Intel's next major offerings during this period was the Intel 8008. A key feature introduced in the 8008 was the indirect addressing. To understand this, let's first look at the direct addressing. In direct addressing, an instruction specifies the exact memory location where the data is stored. The CPU then goes straight to that address and retrieves the data. Indirect addressing, however, it adds another layer of flexibility. Instead of pointing directly to the data, where the instructions points to the memory location that contains a pointer, and the pointer tells the CPU where the real data is stored. Excuse me. This might sound like an unnecessary extra step, but it allows programs to be far more dynamic. It means that data can be moved around in memory without rewriting large parts of a program. In another major addition to the 8008 was the introduction of interrupts. Interrupts allows the CPU to temporarily pause what it was doing and jump to a higher priority section of the code. This could be triggered by hardware signals such as keyboard presses, a real-time clock tick, or even an internal CPU events. Software could also trigger interrupts, of course. To visualize this, imagine you're writing an essay, and suddenly your phone rings. You stop writing, answer the phone, then return to your essay right where you left off. That's essentially what an interrupt allows the CPU to do. After the interrupt service routine finishes executing, the CPU resumes to the original program. This feature made computers far more responsive and interactive, paving the way for real-time input for devices like keyboards, mice, and eventually graphical interfaces. Following the 8008s, Intel released the 8080 or 8080, which was a major step forward. The 8080 introduced the use of an external bus controller. This separates support chip-handled communication between the CPU and the other operating system components or other system components such as RAM and input or output devices. This separation was important because memory and I/O devices often operated at slower speeds than CPU itself. By offloading these tasks to a dedicated controller, the CPU could run faster without being bottlenecked by slower components. This also improved electrical noise immunity and made systems more reliable. Many historians consider the 8080 to be the first truly usable microprocessor for general purpose computing. However, Intel was not alone in this race. Around this time, the competing processor designs were excuse me, emerging. One of the most significant competitors was the Zilog Z80, which ironically was designed by Federico Fagin, a former Intel engineer. The Z80 was essentially an enhanced version of the 8080, and it became extremely popular in early personal computers. Excuse me. To counter this, the Intel released the 8086, a processor that would change computing history. The 8086 introduced major improvements that made it more suitable for higher level programming languages. One of these was improved stack support. In programming, commonly used blocks of codes are grouped into what we call subroutines, also known as functions, procedures, or subprograms. Uh, excuse me. Subroutines, also known as function procedures or subprograms. These are reusable sections of code that perform a specific task. For example, imagine you're writing a program that calculates the average of thousands of number pairs instead of rewriting the same code over and over again. You create a subroutine that takes two numbers, calculates their average, and returns the result. Your main program then repeatedly calls this subroutine. The stack is what makes this possible. It stores return addresses, functional parameters, and temporary data, allowing the CPU to jump in and out of subroutines smoothly. The growing complexity of 8086 also marked Intel's firm commitment to a design philosophy known as the CISC, or Complex Instruction Set Computing. Excuse me. CISC processors use a wide variety of powerful and specialized instructions. A single instruction might perform multiple low-level operations at once, making programming easier in some cases, but it also makes the CPU itself more complex. In contrast, most modern processors use RISC, or Reduced Instruction Set Computing. This architecture relies on simpler instructions that execute very quickly, often in a single clock cycle. Interestingly, the x86 processor